Hello everyone, welcome again to our introduction to remote sensing of the environment. This is our third lab of this introductory course, and today we're going to move on from spectra to exploring some indices and focusing first on finding the right image. The objective of this lab is to gain understanding of a range of spectral indices and develop the skills for calculating any index that you require. But before getting to that, we'll build on last week's lab and learn how to find an image for a particular geographic location of interest. So we will, of course, be using Earth Engine again. So open up your Earth Engine environment in your web browser. And for today's lab, we'll be navigating to the city of Darwin. And to do that, we can simply type Darwin in the search bar, and that's Darwin in the Northern Territory of Australia. This is the city of Darwin, and I'm speaking to you from Charles Darwin University, which is located over here, just to the north of Rapid Creek. Now, our next step is to use the geometry tools to make a point on the map, and this will be the point that gives a geographic location, geographic coordinates, to help us refine our image search. So to do that, we use the little teardrop icon. That's the one located over here. In coming weeks, we'll look at using the other vector tools. So if you add a marker, it opens up this little drawing environment, and you can just click on the map, puts in that marker. Now the important thing to note is that in your empty script up here, it's added a variable called geometry, and you'll see it has the coordinates of that point. We can exit, and if you want to switch that off and on, you can do so over here. This is the layer manager for your geometries, your point and area shapefiles and tables. Coming down to step 3, we're going to rename this resulting point campus because it's located on our campus. So I do that over here and type enter, and our variable is now called campus. Be careful with what you call this, because if you're going to be using it in a script later, you need to refer to it. It matters what you call it, and if you make use of capital letters or not. We'll also be using Sentinel-2 imagery again. Love Sentinel-2, fantastic multispectral satellite. So let's type Sentinel-2, and you'll see this pop up. This is quite exciting. For a long time we've been using the level 1C products, and Sentinel-2 level 2A has just become available, but for today's lab we'll continue using the level 1C products. Import that, and you'll see that it's now imported the image collection of Sentinel-2. We're going to rename this collection Sen2 for simplicity when we are referring to it later. Okay, so we've done that step. Number 6, it's important to understand that we have now added access to the full Sentinel-2 image collection. That's every image that's ever been collected to date across the entire globe to our script. We've only added the access, not the actual images. We don't want to load all these images, we just want to find a single cloud-free image over Charles Darwin University. And as such, we can now filter the image collection with a few criteria, such as the date of acquisition, the spatial location, and cloud cover. To achieve this, we need to use a bit of coding. In the JavaScript programming language, remember that 2 forward slashes indicate comment lines and are ignored in actual processing steps. We use these 2 slashes to write notes to ourselves so that we and others who might want to use the code can understand why we've done certain things. Let's copy the code in and then we'll discuss it in the code editor. So let's paste that in, give ourselves a bit more room. Okay, now let's look what we've done here. On our first line, we're making a new variable called image. Remember that this send2 is the image collection. If we want to pull out just one image, we need to create a variable. So variable image equals earth-engine dot image. Send2 means we want that image to come from this image collection. The way I've broken up the code here is so that the comments are embedded, but we could write this code all in one line. So this dot would continue straight on from here. Okay, so this is this line. We've created the variable and we're calling the image collection. Next, we want to filter by a particular date range. So we use dot filter date. Be careful with the capital D. Filter date, we put in a start date and an end date. This is using the American date syntax. Next, filter bounds. This is now a spatial filter. This step was a temporal filter, filtering by time. This is a spatial filter. We're saying that we want to filter the collection to intersect with this marker. Filter bounds campus. We called our geometry campus, so we're going to filter only images that intersect this point. Next, we're going to sort the collection by a metadata property. Now, in the Sentinel-2 information sheet here, you will see that we have in the image properties a metadata field called cloud coverage assessment, and this is a cloudy pixel percentage for the whole archive taken from the original metadata. So what we're going to do is we're going to filter the collection by date, then by spatial location, and then we're going to sort it from the least cloudy to the most cloudy image within that date range. And then we're going to ask Google to pull out for us the first image. That's what this first means. So we just want, in effect, this will be the least cloudy image. And we'll print this to the console. We'll give that a name, a Sentinel-2 scene. This can be whatever you type between these markers will be the name that comes up in the console. So let's run that, and we'll see that our script has returned a single image from the 19th of June 2016. If we want to map that, we will use the map add layer command like we've used before, but something a little different to last week. You'll remember in our previous labs, we've used map add layer, and we've defined the visualization parameters within this command. But what we're going to do now is we're first going to define the visualization parameters up front. We're going to define a variable called true color, and we're going to specify that for true color, we make use of bands 4, 3, and 2, that is red, green, and blue, with a min of 0 and a max of 3000 for Sentinel-2 1C data. And then when it comes to map add layer, all we need to do is specify the image we want to map, the visualization parameters. We can just use the name true color and give the layer a title. So if I copy this bit of code and paste it here, run that, we should see true color image pop up in our layers tab, and here it comes. And this is a very nice cloud-free image over Darwin. Now, the really powerful thing about this approach is that once you have this bit of code, and I suggest you save it, and this is our lab 3. Once we have this bit of code, been using these dates here, but if we wanted a more recent image, we could change this to say 2018. Just hit run, and straight away it will pull up a newer image for us, this one from the 4th of July 2018. Importantly, our image search is dictated to intersect with this little dropper. So if we wanted an image somewhere else, like over Kakadu National Park, for example, we could just click on here once to make it active, then click and hold. We can drag that dropper somewhere else, just hit run again, and our image will pop up in that region. So once you have this code, it's extremely flexible. You can just adjust the date and adjust where you put the dropper to match your needs. Okay. Step 12 is creating the false color composite. And like we did before in our previous step, we're now defining a variable false color. In Sentinel-2, the near-infrared band is in band 8, so this will be a near-infrared false color composite. We're going to put band 4, red, into the green channel, and band 3 into the blue channel. If we run this, we'll have 2 layers now popping up, the true color image underneath and the false color near infrared on top. Remembering that this false color composite really pulls out the photosynthetically active vegetation. Okay, but just read through and remind yourself of some of the steps we've been doing. Practice with different visualization parameters from last week. Then you can move on to calculating NDVI. So we've covered this in class. NDVI is the normalized difference vegetation index, and it's calculated from the red and near infrared bands according to this equation. NDVI equals near infrared minus red divided by near infrared plus red. Paste the following lines, click run. Let's just read through what we're doing here. So a little more complex now, but once you've created this, you can use it in any example going forward. And you can also use this format to make other indices based on other equations. So we're going to create a variable called NDVI. NDVI will equal image. That's the image that we've pulled up, dot expression. And the expression is near infrared minus red divided by near infrared plus red. But in this part over here, you'll notice we've just been using words here, near infrared, red, and this is where we're defining them. We're specifying here that red is, we're going to, from the image, select band 4, because that's the red band. NIR, image, select band 8, because that's the near infrared band. Blue, image, select B2, because that's blue. And then we will map add layer, NDVI, that's the variable we've created, with a min of 0 and a max of 1. It is possible to have a negative value, but that will always be in a water body. So if we're mapping vegetation on land, we would just use a min of 0 and a max of 1. And we're going to call this layer NDVI. Again, it can look complex at first, but once you have it, it's a great basis for developing other indices or implementing other indices. So let's run that. And up pops our true color, false color composite, and the NDVI should map out on top. And it's a grayscale image and mapped from black being 0 through to 1. And you'll see that these riparian and mangrove areas are showing up as the brightest values. If we want to actually look at the NDVI values, remember we can use the Inspector tab here. Click on the image. That will bring up our spectral response curves, but it will also down here give us the NDVI value. So in this case, 0.7. So that's close to the maximum NDVI we can achieve. If we come off in the savanna woodland somewhere over here, you'll see that it's considerably lower, 0.27. Okay, I'd like you to explore different parts of the image, see how NDVI values vary with different substrate types. And remember that if you want to explore a completely different region, you can just grab your dropper, drag it off somewhere else, hit run, and wait for that image to come up. This is an example now of a Limon National Park out into the Gulf of Carpentaria. A few other points to remember is that if we would like to change the color here, we're currently using a grayscale color scheme. We can add in a palette over here within the visualization parameters of NDVI. For example, if we type palette, and this is from, we did cover this in lab 1, in between square brackets we can define some colors, say go from brown through to green, and if we click run now, if I did that correctly, it should now map out our NDVI map with a color stretch from brown to green instead of the default black to white. Let's just wait for that to load up. That looks pretty good. Let's maybe just move our dropper back up to this part of the world and look at our date range. This is quite a dry time of year. Let's search for an image in the earlier part of the year. Just at the end of the wet season, might get something a bit greener popping up. I want some coastal vegetation, so I'll just move that slightly. Hit run again. Now if I zoom in, you can see it's the wet season, and here comes the NDVI map on top. That's pretty good, but the two colors, we're losing a bit of detail. So I'm going to add in here another color. I'm going to put in yellow. Put an extra marker like that. And now we'll have a color scale going from brown through yellow to green for the NDVI. And that looks a bit better. That's giving us more variation So that's just a quick recap on how you can use palettes when you're mapping out variables. And keep in mind that you can use this approach to define any variable. We spoke in class about enhanced vegetation index or normalized difference water index. Once you have the equations, just write the equation in here and then specify which bands must be used in this portion. Now, for the rest of the lab, it's a practical exercise, and I've asked you to search for a cloud-free Sentinel-2 image from May, July, and September 2018. So I want you to pull up 3 different Sentinel-2 images collected over Litchfield National Park. It's located south of Darwin near Bachelor. And I want you to calculate NDVI for each of these scenes, load up the 3 scenes into the map view, and inspect how NDVI varies spatially across the image, how they vary, and how NDVI varies according to time of year. A couple of hints. We've called this in this early part of our course, we've called this image, and we've specified the dates. If you're looking only in the month of May, you can adjust these dates to be from the 1st of May until the 30th of May. The code will pull out the most cloud-free image in that month, but it would be a good idea to then call this May image, for example. But be aware that if you change this name, you need to change it wherever else you have used it in the code. The second part is a bit more complex. I've asked you to repeat this process, but instead using Landsat 8 imagery. Now, if we come back here, search for Landsat 8. It's important to type the 8. There's so many Landsat options. This will reduce your selections. And we're going to use Landsat 8 surface reflectance tier 1. A couple of important points to note when you're pulling in the Landsat imagery. You can largely just adopt the script that we've developed using Sentinel-2. You'll need to import it and name it as a variable. Some important things to note though is that the band combinations will be slightly different. And if we look through here, you'll see that in Landsat 8, the near-infrared band is actually band 5. We jump straight from the red band 4 to the near-infrared band 5. Landsat 8 doesn't have all the red edge bands that Sentinel-2 does. So when we've been working through our code and we've been specifying band 8 as near-infrared, when we're using Landsat 8, you need to be aware that this needs to change to band 5. Something else to be aware of is the spatial resolution of the different sensors. If we look at Sentinel-2 here again, you will see that in the visible range and in the near-infrared range, the spatial resolution is 10 meters. Just make sure you find out whenever you're using a new sensor, be aware of what the spatial resolution is. And if, for example, you find differences in NDVI values between the sensors, you need to think about which wavelengths the bands represent, as well as the spatial resolution. As the spatial resolution changes, the area that you're sampling and the energy available for recording is also changing. So please give that a try. Another thing to note is that up here in our script, where we sorted by cloud coverage assessment, that's how Sentinel-2 filters its cloud. That's the metadata property for cloud cover in Sentinel-2. But I've put in a note here for you that in Landsat 8, the property is slightly different. It's just called cloud cover. So good luck with that. Let me know if you have any problems, and I'll see you next week. Thanks very much. Cheers.